It really is the greatest pleasure and honour for me today to introduce our speaker, Michael Perryman. We both worked over many years for the European Space Agency on astronomical projects that have resulted in dramatic and sometimes radical enrichment of our knowledge of the universe in which we live. In contrast to the small part that I played in the Hubble Space Telescope mission, Michael, if I can blur the gender issue a bit, was the midwife who transformed the near stillbirth of ESA's Hipparcos Space Astrometry mission into the remarkable success that resulted in the publication at the beginning of this millennium of history's greatest star map. The richness of these results and the way they touch on so many aspects of our physical cosmology made it possible for Europe to select, design, build and launch the much more ambitious Gaia satellite that is, as we speak, providing an extraordinarily precise, static and dynamical map of our local patch of the universe. Proposed in 1993 by Perryman along with Lennart Lindgren from Lund in Sweden, Michael parented this mission through its long gestation to craft the Ordnance Survey map of the Milky Way and its near neighbours. I'll leave Michael to tell the story that follows so directly from the journey commenced by William and Caroline Herschel in Bath in the late 18th century. Thank you, Michael.
Thank you. Good evening, everybody. Good evening to the members and officers of Brilsey and of the Herschel Society, and to all of you joining this event tonight. My particular thanks to Tony Symes for organising this. I think it's had one of the longest waiting times of any talk that I've given. It was started back in September 2019. So thank you, Tony. There's a lot of work that goes on behind the scenes in putting this together. And thank you, Bob, for those kind words of introduction. I know that a number of people have joined who have had some involvement in the story that I'm going to tell this evening. So that's a great pleasure. It's wonderful to see them. But my talk is primarily for people who have only perhaps the very vaguest idea, if any at all, of what Hipparcos and Gaia are. I think it's a big story. I hope you'll find it an interesting story. And it's something that I think I quite enjoy the idea of informing a wider public of the results from these missions, which are perhaps rather specialized, but impact on many areas of our understanding of the universe. Now, it's a very big story that I'm going to try and tell this evening, so it's going to be compressed. It covers two space missions, Hipparcos and Gaia. And it covers a field, a span of science, which is preoccupied thinkers and scientists for several thousand years. The story that I'm going to tell is a continuing journey in measuring the distances, the positions and the distances to the stars, something that perhaps started 5,000 years ago with the great Neolithic monuments of things like Newgrange and Stonehenge, aligned with certain celestial phenomena. But it extends all the way to Gaia, launched in 2013, and certainly one of the most, if not at the moment, the most advanced space telescope of the 21st century. This is Gaia itself. You can see the immense size of it. It's 10 meters across, and it's central to the story that I will be telling this evening. But I want to cover 5 real different areas that will be drawn together in this talk. The first is to look at the history of measuring star positions. For a couple of thousand years, astronomy was astrometry. The only area of science accessible was measuring star positions, so it has a very important role in the history of astronomy. I'm going to take you on a quick tour of that, and then that leads us to why observations were actually made from space. And that's the story of the first mission, Hipparcos, which was launched in 1989. I'm then going to take a little bit of a break from positional measurements and just give a little interjection on cosmology. What is the big picture that we have on cosmology today? And that's extremely relevant because we'll see that the second mission, Gaia, launched in 2013, picks up on some of the very critical central themes that are central to cosmology today. So I'll then go on and talk about the Gaia mission, just in outline, touch on its technical complexity, and show you some of the scientific results that we're getting from the mission. So first off, the history. Why is measuring star positions important? What can star positions possibly tell us about our place in the universe? I think there's no doubt that our cave-dwelling ancestors would probably be surprised to hear that you can look out, measure the positions of the stars, and end up figuring out the age of the universe, the size of the galaxy, the distance to the Large Magellanic Clouds, and many, many other things are centrally dependent on our ability to measure star positions and distances. So this is my starting theme, the history. The curious motion of the planets as the Earth moves in its orbit, and we look out and look here at the orbit of Mars. You can see at this moment Mars is moving forward in a prograde sense, but suddenly stops, moves into a retrograde sense, and then proceeds again. And this has a natural explanation in the sun-centered system, but 2,000 years ago, the ancient Greeks, who in general believed that the Earth was at the center of the universe, could only explain the motion of the planets through this very complex epicyclic motion, that the planets moved on circles which themselves rotated in circles around the Earth. We now know that this was wrong, but it took 1,500 years for that realization to take firm hold. So if we go back 2,000 years, we've got the ancient Greeks. They were able to hazard guesses about the distances of the sun and moon, and they were preoccupied with examining the motion of the planets. Historians today acknowledge the great part that the burgeoning Islamic culture and Chinese cultures had in the understanding of positional measurements and star catalogues. To the Islamic culture, for example, star positions and timing was very critical for the determination of the direction of Mecca, the timing of Ramadan, things like this. A huge chapter in the history of science, which I'm going to give just 3 lines to, was the whole resurgence of scientific inquiry in Europe starting around the 1500s, 1600s. The enormous achievements, intellectual achievements, that the Earth moves around the sun, much better astronomical observations typified by the great Tycho Brahe, the Dane Tycho Brahe, the understanding of the motions of the planets explicable empirically in the form of Kepler's laws, and more in terms of physical laws, the Newton's laws of gravities and motion. And this whole period saw great advances in determining star positions, charting the stars, compiling the positions of them. And this was dominated, this was underlined by very practical requirements, the requirement of being able to navigate at sea, which underpinned the determination of accurate star positions. Moving forward, Edmund Halley of comet fame in 1718 was the first to discern the motions of stars actually moving through space. 1725, James Bradley, one of the Astronomers Royal, measured stellar aberration. This is an interesting phenomenon which arises because of the velocity of the Earth around the sun and the addition of the speed of light. He was trying to measure the distance to the stars. He was trying to measure parallax, ended up with stellar aberration as a byproduct, a very important milestone in understanding the Earth's motion, the finite speed of light, and the immensity of stellar distances. And then in 1783, Herschel himself, examining the motions of many stars and realizing that the sun itself must be moving through space. So let me just show you that in a little bit of a caricature. This is Edmund Halley. He'd been looking at the stars, and here we are looking at Aldebaran. And Halley noticed that Aldebaran, as well as Sirius and Arcturus, were significantly displaced from the positions that the ancient Greeks had measured 2,000 years before. The first realization 300 years ago that stars were actually moving through space. Now, as soon as there was the acceptance that the Earth was moving around the sun, came the realization that it should be possible to measure the distance to the stars using the effect of parallax. Parallax is the effect, if you close one eye, close the other eye, look at a nearby object, it seems to jump backwards and forwards compared to a background object. And exactly the same phenomenon is true as the Earth goes around the sun. In this little image here, we see the Earth on two sides of the orbit around the sun. And if you look at a nearby star and project it against the background stars, then the nearby stars appear to move compared to the background stars. They don't actually move, they appear to move because the Earth is moving around the sun. But the fact that the Earth is moving around the sun means that one should be able to, astronomers should have been able to measure parallax of nearby stars. Now, there are many complications to this simple picture. The sun, for example, is itself moving through space. All the other stars are moving through space. All these stars have their own distance and therefore their own parallactic motion. And there are many other complications as well. But the essential point is, as the Earth goes around the sun, nearby stars appear to move with respect to the background stars. And if we can measure that, we can use simple trigonometry to determine the distance to the stars. The problem that we face, or the astronomers 300 years ago faced, was the sheer size of space. And I'm going to spend one view graph and a couple of slides just trying to illustrate this, how enormous and therefore how difficult the task actually is. So we'll try it in the following way. Imagine the sun is shrunk to the size of a marble, so 1 centimeter in size. Then on that scale, the Earth would be a grain of salt moving around in an orbit at a distance of 1 meter. Pluto would lie out at about 40 meters. The nearest star to us would then on this scale be at around 200 kilometers. And the center of the galaxy, for example, at 8 kiloparsecs, 8,000 parsecs, would be roughly 10,000 times that distance. And the whole problem then of trying to determine star distances is one of trying to measure these tiny, tiny angles on this scale, the Earth moving in an orbit around a meter, trying to determine the distance out at several hundred or several thousand kilometers. This was an extremely long and extremely protracted scientific journey. It took scientists, astronomers, 250 years from the moment that they first started trying to measure the parallactic motion of the nearest stars until the point in time in the late 1830s when 3 scientists, Friedrich Bessel, Thomas Henderson, and Wilhelm Struve, more or less reported at the same time, or very close together, the parallaxes of the nearby stars. It's a very long, very interesting journey, dominated by attempts to measure smaller and smaller angles, and eventually culminating in the realization, the determination of the first stellar distances. And for this, Bessel was awarded the Royal Astronomical Society's gold medal, and the president, Herschel, at the time said that this was the greatest and most glorious triumph which practical astronomy has ever witnessed. I'm going to give 2 other attempts to illustrate the immensity of space. This one is due to Herschel. He said that to drop a pea at the end of every mile on a voyage on a limitless ocean to the nearest fixed star would require a fleet of 10,000 ships, each carrying 600 tons of peas. Now, I don't know how easy it is for you to visualize 600 tons of peas and 10,000 ships dropping a pea at every mile. I think the only thing you can really conclude from this is that space is very, very big. I have another analogy. The world's population of 7 billion people would reach the next nearest star to us if they each was spaced by 5,000 kilometers. So 5,000 kilometers, repeat it 7 billion times and you get to the nearest star. Now, one thing, I'm going to race over 100 years of astronomical developments, and just to try and make the following simple point. In the last 100 years, astronomers have built bigger and bigger telescopes, and they have, of course, been extremely successful in measuring fainter stars. Spectroscopy has developed enormously, and observations at radio, X-ray, infrared wavelengths, and so on and so on. And we can trace that very quickly through grand programs like the Astrographic Catalogue, which occupied 20 observatories for 40 years around the 1900s, creating a celestial sky map. Back in the day, these measurements were all made by hand, recorded by hand, and computed by hand. As one moves towards the second half of the last century, these great Schmidt telescopes came to the fore and started making great surveys of the sky, going down to 20th, 21st magnitude, and recording enormous sky surveys. And it brings us almost to the present day. The European Southern Observatory's telescopes, the 8-meter telescopes in Chile, there are 10-meter telescopes, 1 or 2 10-meter telescopes elsewhere around the world. But for the purpose of this talk, these telescopes all have one thing in common, and that is the following. It's a slightly negative side of them, but it remains all but impossible for these telescopes to measure stellar distances from the Earth beneath the twinkling atmosphere, beneath our Earth's twinkling atmosphere. And although I'm not going to go through a lot of arguments for this, I want to stress the point that almost every aspect of astronomy depends at some level on a knowledge of star distances. It's not always been possible to determine these trigonometrically through the measurement of parallax. A lot of indirect methods have sprung up and been developed to determine the distance scale within our galaxy, but measuring trigonometric parallaxes remains the most central, the most fundamental, and the most direct way, the least unambiguous way of determining distances. So again, just to show that schematically, there we are sitting on the Earth. Starlight propagates through the essential vacuum of space as plane waves, but as it comes through our atmosphere, the phase fluctuations of the atmosphere result in twinkling starlight, which affects both the amplitude of the starlight, which gives rise to the twinkling, and also the phase, the positional measurements, which prevents us from measuring the positions very, very accurately. Hipparcos, the first mission that I will talk about, gets down to about 1 milli-arcsecond, 1,000th of an arcsecond. To put that in perspective, with the human eye, we can resolve angles of around 30 arcseconds, or one arc minute, 60 arcseconds. To go down to 1 arcsecond and then down to 1,000th of an arcsecond as measured by Hipparcos, 1,000th of an arcsecond would correspond to something like the size of a golf ball seen from where we are today, sitting on the Empire State Building, or the size of an astronaut standing on the moon's surface as seen from the Earth. That is the angle of about 1 milli-arcsecond that we targeted with Hipparcos. So let me just then, that's my historical introduction, and I'm going to now say a few words about Hipparcos, the first satellite, the first mission that was dedicated to measuring star positions through space, in space. The first ideas for making these distance measurements, these parallax measurements from space, came from a French scientist, Pierre Lacroute, in 1967. I think it's interesting looking back historically that this proposal for such an advanced satellite was just made just 10 years after the launch of Sputnik 1. Hipparcos was accepted as a project by the European Space Agency in 1980. It was developed between the years 81 to 89, launched in 1989. It was operated for 4 years, and it created a catalogue of 120,000 stars, accurate to something like 1,000th of an arc second. So something like 100 times or 500 times better than one can observe distance angles from the ground. The catalogue was the final catalogue was released in 1997, and thousands of scientific papers have been published based on these distances and star motions since. Now, to try and clarify exactly what it is we're measuring, this schematic, I'm looking at one star in the sky. Imagine we're looking at one star, and we're going to look at it under a massive celestial magnifying glass, and we're going to watch how it moves with time. And if we could see that with clarity and with precision, we'd see that star moving through space in a certain direction because of its own motion through space. And we'd also see the star position performing these loops as the Earth goes around the sun. So the loops that you can see there are the effect of parallax. It's nothing to do with the star's motion itself. It's to do with the Earth's motion around the sun, which is reflected in this parallax. And then you see the effect of the star motion through space. These would be observations extending over 3 years. You can see these 3 separate loops as the Earth is going around the sun. So if we could look at one star under a celestial magnifying glass, it would look like that. Now let's have a look at, let's apply our magnifying glass to 3 stars, 3 arbitrary stars in the same region of sky. And we might find that they're moving in different directions, of course, and they're very different distances, of course, and therefore their paths through space are in different directions, and the amplitude of their parallax curves are very different. Here we have a nearby star exercising these large parallactic loops because it's near to us, and there's a more distant star moving in a different direction with a very small parallactic amplitude because it's lying at a very large distance. Now, the secret of Hipparcos and indeed Gaia is to use 2 separate viewing directions. The satellites themselves have 2 telescopes that look out in 2 widely separated viewing directions, about 60 degrees in the case of Hipparcos and about 100 degrees in the case of Gaia. I'm not going to go through exactly why this is so, but what it allows us to do is to measure the absolute distances, the absolute parallaxes, with respect to some absolute reference system. I probably have lost most of you in that last attempt to explain why we have 2 viewing directions, but the end result is that if we just imagine now 6 stars in my little schematic, 3 coming from one field of view, 3 coming from another field of view, and we set our observations in motion. Now, all kinds of things are going on. These stars are moving in different directions because they're moving through space in different directions. They're all exercising their parallactic curves in different ways because they're coming from different directions and they're at different distances. And it does look from this as if we have an almost intractable problem to solve, because the positions, if we propagate forward a few months, the positions have changed completely in a completely different configuration. But the key point is that those very complex changes in positions are just determined by a very few number of physical parameters. Each star is described by just 5 parameters: its position, its motion through space, and its distance. And adding all of those together can gives you these very complex motions, which we measure with the satellite, which we send to the ground, and which we recombine this a sort of giant celestial jigsaw on the ground. So coming back to Hipparcos, I've found this old archival photograph from 1965, one of the first meetings to discuss the prospects of measuring star positions from space. The actual implementation, the design, the technology development was executed along with all the other satellite missions of the European Space Agency at its technology center in the Netherlands. This is Noordwijk in the Netherlands. And this is the sort of nerve center, the technology center, the management center of all of the ESA missions, whether they are meteorological, Earth observation, solar system, space, human space flight, and so on. The heart of Hipparcos was this curious mirror. It is only about 30 centimeters in size. It's not obvious from the scale here, but the diameter is only about 30 centimeters. But it was an extremely advanced piece of optical engineering. It was a very complex, very challenging piece of the central experimental heart of the Hipparcos mission. Two of these mirrors were constructed. The flight spare actually sits in the National Maritime Museum at Greenwich, and you can go and view that. It's labeled there, and it was the spare of the unit. And I'm delighted to see that one of the people that played a central role in bringing this particular piece of optics to fruition is actually joining us this evening for the presentation. This is the satellite being integrated in 1987. 2 years before launch. This is the satellite undergoing some testing in the European Space Agency's Large Solar Simulator. You can see there the solar panels. These are pointing towards the sun. The satellite is going to rotate about an axis along here, and the two satellite viewing directions poke out from the satellite here. Now, just to give you some excitement, we're going to sit through the launch of Hipparcos in 1989.
8, 7, 6, 5, 4, 3, 2, 1, mise à feu.
We have a beautiful shot of those Viking engines as Ariane 4 lifts off its launch pad and roars into the night here above Kourou.
It is perhaps difficult to imagine that after 8 years working on a piece of very advanced, extremely delicate optics, you consign it to the top of this 60-meter tall rocket, which is fired off into space. The whole ground vibrates for miles and miles around. And somehow you cross your fingers and hope that the extremely talented engineers that have put this beast together have actually done their job correctly. Indeed, they had. The launch went off flawlessly. The instrument operated flawlessly. The problem was Hipparcos was ended up, for various reasons, the apogee boost motor didn't fire. And for anyone who recalls astronomy back in 1989, Hipparcos became high on the news headlines, not for the reasons that we had hoped, but because there was the perception at the time that the mission had been lost. Again, it's a long story and another story about how we recovered from that. The fact is that the satellite went on to become extremely successful and not only measured all of the stars that we had set out hoping to measure, but measured them a factor of 2 better. We ended up with a positional catalogue accurate to about a milliarc second, 1,000th of an arc second, compared to the initial target of 2 milliarc seconds. It may not sound a great difference, but it was an achievement, a great achievement, and it meant that the scientific goals of Hipparcos were really underpinned. Now, I'm not going to talk about the science from Hipparcos, because to some extent that is superseded by what's coming out of Gaia. But I would just like to show you, let me spend a couple of minutes on this. It's a sort of animation in the sense that it's been reconstructed. It's reconstructed from the magnitudes and the motions and the parallaxes that we measured from the Hipparcos observations themselves. Hipparcos didn't take photographs, so we're not taking a photograph of the night sky. It made some complex measurements which charted how the stars are moving and how they appeared to be moving. And what we've done here is to reconstruct an animation of the stars in the field of the Pleiades Cluster over a region of about 6 degrees by 4 degrees. So if you were to look on that, the full moon would be, I don't know, a region something like that. We've got Aldebaran here, the bright star, which is in the foreground of the Hyades. And Hipparcos made these measurements, made the measurements of the distances to the stars and the motions of the stars over a lifetime of about 4 years. What I'm doing here is to reconstruct their motions over 60,000 years. The motions are so infinitesimally small that, of course, you can't discern these. Of course, you can't discern these with the naked eye. Star positions seem immutable, unchangeable, even over a human lifetime, but we can measure them with this kind of accuracy, and then we can propagate them over 60,000 years. And in this first animation, I will show you what happens over 60,000 years. If we could come back in 60,000 years' time, this is how the stars are moving. What are we, 10,000 years in now? 20,000 years, you can see some stars moving quite quickly through. You can see the main bulk of the Pleiades cluster moving from right to left on your screen. As I say, Aldebaran is not a member and it's moving, it's in the foreground. So that showed how the stars are moving through space as measured from Hipparcos. The next animation shows the effect of the parallax. Now, just taking the parallax into account, we can animate how our view of the sky would appear, again, if the parallax is accentuated, magnified many, many thousands of times, and it would look like this. So the nearby stars are moving with respect to the background stars, and that oscillatory motion has a period of 1 year as the Earth orbits the sun. So we're viewing, again, this takes us back to my introduction to the topic. As the Earth goes around the sun, we're measuring this from the satellite, but we're measuring the difference in star positions with respect to the background stars because of the effect of parallax. Now we can put those two effects together, and in the third animation, I will show you the combination of the 60,000 years of proper motion combined on a different time scale, of course, with the parallactic motion. And what you would see then is the stars performing this backwards and forwards oscillatory motion due to the parallax, and then moving through space as a result of the star's motion through space itself. So this is a reconstruction from the real observations that we made with Hipparcos, and I think it's a very nice illustration of the way in which the star positions are changing, one with respect to the other, which underpins the very way in which we make the measurements from the two satellites. I will do the same now quickly with the Pleiades. The Pleiades, the seven sisters, again, visible to the naked eye. This is how the constellation, this is how the cluster would appear if we could monitor its motion over 150,000 years. You can see some stars moving very rapidly through space. These are nearby stars, perhaps halo stars. This is the Pleiades cluster itself, all participating in the same uniform space motion as the cluster, which is gravitationally bound set of stars, moves through space. The effect of the parallax is only similarly. I'm showing here just the effect of the Earth's motion around the sun, the nearby stars appearing to move more than the background stars. And we can put those two effects together and see now, if we add the proper motions to the parallax, they will move in this complicated way. And again, this is exactly what we're measuring through these snapshots of observations through Hipparcos and with Gaia. Don't make any serious attempt to try and understand how we could possibly make those measurements. You know, that is another very detailed story. I just want to get across today that that is possible, and it's possible with this kind of level of precision. Now, so much for Hipparcos. Hipparcos created a catalogue of 120,000 stars, accurate to 1 milliarc second. It transformed positional measurements. It transformed our knowledge of the distance scale. It made very big contributions to the knowledge of how stars move with respect to the galaxy. And it set the scene for the massive technical improvement and the massive scientific improvement that was possible with Gaia. But what I want to do is just take a little interlude, a 5-minute interlude, and try and show you now what happened really in the intervening years. Cosmology was making massive progress, and I'm going to try and show you what is the big picture of cosmology today. And what we'll see from this is that the big progress that's been made in cosmology sets a very different background panorama for the observations that Gaia is currently making. That will become clear, I hope, to you in just a few moments. So the next couple of slides, in a sense, nothing to do with Hipparcos, nothing to do with Gaia, nothing to do with astrometry. It's just where we are with cosmology. And I won't take any questions on cosmology, because when it comes to dark energy and dark matter and singularities and things like that, you need to ask somebody else. But I can tell you what is the party line. If we could see our own galaxy from a distance, it would look something like this. This is Andromeda, and we are sitting way out in one of the spiral arms. We're out here. We're about 8,000, 10,000 parsecs, something like 30,000 light years. It would take light 30,000 years to get from where we are to the center. Hipparcos measured out to, it's a bit hand waving, we can't say a precise distance, but sort of out to 100 parsecs, out to about 300 light years. So on the scale of the galaxy, the sphere of influence that we were able to measure with Hipparcos took us well out from what was possible from the ground, but on the scale size of our galaxy, it was still almost microscopic. This is the sphere of influence that we had with Hipparcos. Gaia is something different. It extends our knowledge of distances and motions really out to distances on the scale size of our own galaxy. This is a very, very simple animation. I made it 20 years ago, and I still think it's quite good. Our galaxy, just to fix in your mind, our galaxy rotates something like this. This is a simple schematic. It's a face-on view. Our galaxy has got fairly uniform rotation. It takes about 250 million years to rotate. Stars bounce up and down with a period of about 50 million years. And all of this is controlled by the mass in the galaxy itself. That's a very quick animation of what our galaxy looks like in sort of broad features. Now for a couple of, well, where are we with cosmology? I'm not going to go into any details here, but we've got this picture now that the universe started about 13.7 billion years ago. It expanded from a high density and high temperature state. The current paradigm is that the universe that we observe is made of something like 5% of normal matter, 20% of dark matter, 68% of dark energy. This remarkable picture, bewildering, perplexing though it may seem, has got enormous explanatory and predictive power. It explains the origin and abundance of the elements. It explains the cosmic microwave background radiation. It predicts and explains all sorts of things. It doesn't tell us how energy, time, and space emerged. It doesn't tell us anything about the universe before this period of time, 13.7 billion years ago. But I think the truly quite wonderful and remarkable achievements of this picture of cosmology is that it allows us to put together in these wonderful simulations. These are the I'm going to run through very quickly the millennium, what I call the millennium simulations by Volker Springel and colleagues that were published in 2005, run about the year 2000. And what they did was to put together all of the ingredients that we're aware of at that time in cosmology and allow this model to run forward over billions of years. And what we'll see from this is how the structure that we can see around us today, so the galaxies, the cluster of galaxies, the superclusters of galaxies, filamentary streams and so on, actually appears out of these kind of simulations. So let's just sit back and enjoy that simulation, this animation. As I said, this is not Gaia, this is not Hipparcos, this is cosmologists let loose on a massive supercomputer. When you look at the Millennium simulations from 20 years ago, I think it really is stunning, the ability that we now have to understand the structure of the universe around us. This has been even more transformed and even more advanced by the even later and more enormous computations that have been undertaken in the last few years. And I'd like to show you this again. It's a minute and a half. It's called the TNG50. Again, it's led by Volker Springel, but it's a large collaboration of European scientists that have put in basically all of the essential physics that we're aware of that underpins galaxy formation, star formation, end of supernovae explosion, interstellar medium, feedback from the interstellar medium, dark matter, and so on and so on. And this really represents the state of the art in using cosmological models to predict structure within our universe. And the reason I want to spend some time on this is, as I let the simulation go, this is picking out a particular region which is considered to replicate our own galaxy, our own Milky Way galaxy. So let this run. It's going to be 10 billion years compressed into 90 seconds. And as we get towards the end of the movie, you will see something like our own galaxy emerging out of this massive cosmic web of dark matter, dark energy, star formation, and so on. There's some explanatory things that go on as the movie goes forward. So there's the scale. 20 kiloparsecs, it's changing with time. Redshift up on the top right corner, running from a redshift of 8 down to the present day. Bottom right corner is showing a zoom of the central structure. Over on the left, we're looking at the star formation rate going on in the center of this galaxy. So we're now at a redshift of 1.5, about 8 billion years ago. You can see the spiral nature of the galaxy starting to emerge. And what is happening over the several billion years since then is more structure being accreted, more embryonic galaxies being accreted, merging with our galaxy halo. And then a satellite galaxy, a little bit like the Large Magellanic Cloud you see in orbit around a galaxy which roughly resembles our own. Now, I think the great importance, the reason I wanted to put this animation in, is that it starts giving you starts giving astronomers a very clear picture of how our galaxy came into being and the kind of structures that might be accompanying it: satellite galaxies, globular clusters, spiral structure, thick disk, thin disk populations. All of these find some sort of natural explanation in this big cosmological picture. And this ends up being the backdrop against which the Gaia observations are being made at the present time. So I now move to the fourth of my 5 topics, which is to tell you about Gaia. So the second, Hipparcos was the forerunner. The Hipparcos results, the scientific advances and the technological knowledge from Hipparcos allowed ESA to go ahead with this follow-up mission, Gaia. So to put those in context, Hipparcos conceived back in 1968, accepted in 1980, launched in 89, operated until 1993, final results published in 1997. Gaia conceived in 1993, adopted in 2000, launched in 2013. It's operating today. It's will hopefully continue operating until around 2024. I'm not sure what the current estimates of when the attitude control system will run out, something around 2024. And it's going to take quite a while after that for the final results to be processed and put together and the final results to emerge, something around 2030. But let's have a quick look through. Gaia was developed over a period of, depends how you count it, 15 years or so. Launched in December 2013. It was sent to a special quiet orbit, the Lagrange point L2, 1.5 million kilometers away from the Earth in the anti-sun direction. Everything about it really is state of the art. It's a slowly spinning satellite. It spins once every hour, precesses around the sky, observes the whole sky continuously. It sends 5 megabits of data to the ground every second. So it's a vast quantity of data which is being assembled on the ground. And compared to the 120,000 stars measured by Hipparcos 20 years previously, Gaia is in the process of measuring more than 2 billion stars. It's more than 1% of the total population of our galaxy. And successive catalogues are being released. The most recent came out in December of last year, and it's already providing huge advances in understanding our galaxy. I'm not planning today to talk in any detail about this, but it's a big industrial effort, 30 industrial teams involved in it, probably 2,000 engineers at its peak. It's got the biggest CCD detector array of any satellite mission. It's got extreme mechanical and thermal tolerances. It's got the highest data rate and the largest data volume. It's the biggest data analysis problem in astronomy ever undertaken. And there are hundreds of scientists involved in the analysis of the data today. It's generating a very large number of scientific papers. All I'm going to do today is show you a couple of the pictures of the hardware. This is, again, if you can cast your mind back to the 30 centimeter diameter mirror of Hipparcos that I showed you. Here we're looking at two viewing directions, 2 telescopes. The primary mirror is 1.5 meters in extent, 0.5 meter wide. There's another one here that will be implemented. The focal plane assembly sits behind this toroidal structure. This is a massive piece of silicon carbide, which is a very, very rigid, uniform, thermally tolerant structure on which all the optics is mounted. So a very complex piece of optical technology and a very accurate piece of thermal and mechanical control. At the focal plane are 106 CCDs, These are big CCDs. Each of them are 4,500 by 2,000, but they really are state of the art. They're manufactured with extreme tolerances and extremely performant CCDs, and they sit in this big array carpeting the focal plane. And what happens is that the star images, as the satellite spins, the satellite images move across this focal plane array, and the measurements are made using these CCDs. There is the satellite almost fully assembled. Here is the heart in the center. This is the heart of the instrument that we've just seen. There is this massive sun shield, which in the launch configuration is folded up against the body of the satellite. And once the whole thing is out at the Lagrange L2 point, this whole thermal shield is deployed. On the back side is the solar array providing power. And on this side of the satellite, the heart of the payload shielded from the direct thermal input from the sun. And again, for fun, I'm going to let us enjoy the few seconds surrounding launch of Gaia back in 2013.
Top, H0-1 minute.
We're in the final moments of final countdown for the 6th Soyuz to fly from French Guiana. Excitement here has been high all week, as you can expect. Another of those moments now as we approach liftoff. The ignition sequence, 20 engines are lit at once. The ignition sequence is in 3 stages. Part of it is a sequence from minus 17 seconds down to minus 6 seconds, during which the engines are tested. There are the arms rolling away. That's one of the final moments. At minus 15 seconds is the first controlled ignition. At minus 7 seconds is another one at about half pressure. And then at minus 3 seconds, the order is given for the third and final phase. There's the gantry, arms going.
À tous de DDO, attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top, décollage.
So Gaia was sent out to this Lagrange point, a stable, gravitationally stable point, very popular for many satellite missions, 1.5 million kilometers from the Earth. I'll try and show you this figure. There's a lot going on. This is the view of an equatorial view of the entire sky. The blue line is the plane of the ecliptic, so the plane along which the sun and the planets appear to move. As time goes on, the sun will be moving along the ecliptic. The spin axis of Gaia is revolving around the sun at a constant angle, and around the spin axis we've got 2 viewing directions, one here and one here, which are sweeping out swathes on the sky, which are collecting all of these observations, this sort of jigsaw of observations that I showed you earlier on. So let's run through that. It starts off quite slowly. Here you see the spin axis slowly moving. One field of view, the preceding field of view here, the following field of view here, the day counter up here. We've got 2 days. Now I'm going a little bit faster. 30 days, 60 days. You can see what is happening is that the observations are building up more and more, a network of observations over the whole celestial sphere. It's not completely uniform. One cannot make the scanning under the constraints that we had completely uniform, but you can see that over nearly 3 years, a pattern of observations has been built up with many hundreds of observations of the same parts of the sky in different configurations. At the bottom of your screen, you can see the number 0. I just wanted to show you this. If we imagine going back 100 years and imagine the astronomers who were trying to measure parallaxes from the Earth-based telescopes, they would often succeed in measuring 1 star per night, or perhaps 2 or 3 stars per night. If I set this counter going, it shows you how many observations Gaia is actually collecting in the time period of this little animation. So this is the number of observations that we're building up all the time. The latest data release looks something like this. This is a map again of the entire sky, large Magellanic Cloud, small Magellanic Cloud, the galactic center, and this is showing the typical error on the parallaxes over the entire sky. So you can see that many of the mean errors are down around, this is a hundredth of 100 microarc seconds, and very often well below. And as the observations pick up over time, these accuracies are going to improve. So eventually with the final catalogue, when the final catalogue comes out in whatever it is, 2030, there will be a vastly more accurate map. The latest data release then has produced a catalogue which is available for the scientific community to look at already. It contains more than 1.8 billion stars. It's got photometry for 1.8 billion stars. It contains more than 500,000 variable stars, 14,000 asteroids. It's got effective temperatures for 161 million stars, extinction measurements for 80 million stars, radii and luminosities of nearly 80 million stars, radial velocities of more than 7 million. So the numbers are huge. They won't mean a lot to many of you, but they are huge, and it means that our scientific teams, our scientists are being presented now with a huge quantity of very accurate information. Now, I haven't got a similar animation for a Gaia field, but I'm going to take you back and look at the Pleiades cluster. I showed you this before. This is the Pleiades over 60,000 years. And over this 6 degrees by 4 degrees, there will be something about 100 stars. So in this field, something like 100 stars. In the comparable Gaia field, there are about 1 million. And each of those achieving accuracy some 100 times better than we were able to with Hipparcos. On a plot of the accuracies versus time over history, this is time extending back to the time of the ancient Greeks to the present day on a linear scale, more or less linear scale. And here we have accuracy on a logarithmic scale. You can see that from the time of Hipparcos to about the early 1900s or mid 1900s, the accuracies were going logarithmically with time. With Hipparcos, there was a massive leap in accuracy. It's difficult to put that in perspective, but the often lauded and well applauded observations by Tycho Brahe, the factor of improvement of Hipparcos was much greater than the factor of improvement achieved by Tycho Brahe, and the factor of improvement made by Gaia over Hipparcos is the same quantity still. So what we've seen in recent scientific history is this enormous advance in our ability to measure distances and motions. I'm going to run on for 10 more minutes. This was my target. And what I'm going to do in the last 10 minutes, it is an interesting challenge to say, how do I try and explain to interested people, how do I explain what scientists are doing with 2 billion stars? And how can I try and synthesize something like 5,000 scientific papers that have already appeared from Gaia? The only way I think I can do this is to very, very quickly go through a few examples, just touch on a couple of the topics. And I think if you go away with the impression that this satellite mission Gaia is touching science in this area and this area and this area and this area, I think I will have done what I set out to do. It's going to be a little bit of a race, a little bit of a gallop, and it will be for perhaps many of you not very satisfactory, but it will allow you to carry away a picture of some of the advances that Gaia is making. So I've got 7 view graphs, and I will go through them, as I say, quite quickly, and we'll see how Gaia is affecting our understanding of the night sky. So I'm going to work out progressively from the Earth and solar system, working outwards. I'm going to take 3 topics on each page. The first, perhaps a little more mundane, but occultations. We have a very dense network of star motions, and these star motions and star positions are so accurate that objects in the solar system, we can predict when these objects in the solar system are going to pass in front of the particular stars that Gaia is mapping. So it's a combination of accurate observations from the ground and accurate star observations allow us to predict now these occultations. This means that the star paths on the sky can be projected months and years into the future, and occultations of minor solar system bodies by a specific star can be scheduled. Many of those are now underway. We've had the first observations, the first ever observations of Europa, the satellite of Jupiter, giving these as the diameter, major and minor axes diameter of Europa. This is another example that I pulled out, the atmospheric flash on Triton. Triton, the moon of Neptune, has got an atmosphere, and it turns out that as Triton passes across a star, the atmosphere of Triton is bringing the focus of the starlight from the background star to focus, and we see a bright flash in the center as the star passes across the center of the solar system body. I wanted to pick this out. Gaia has not actually, I've not seen a paper on this yet, but there were several papers that appeared with Hipparcos, and I think we'll see something coming out in due course on Gaia. Star observations allow us actually to reconstruct the Earth's motion, the Earth's polar motion. The Earth's spin axis moves through a combination of precession, nutation, and what is called polar motion on shorter timescales. Polar motion was first identified by Chandler in the 1880s, and it may seem surprising that we can contribute anything at all, but the point is that the star positions measured by Hipparcos on the one hand, Gaia on the other, allow the observations that were made from the Earth over the 1900s back propagated, allowing one to determine the motion of the Earth with much greater precision, thanks to the much better observations of star positions that have been made. Earth's climate. Again, I add that because it's a kind of surprising thing that some of these observations can contribute to. There was a very extended cold period in Europe known as the Maunder minimum, which lasted for about 70 years around the years late 1600s, early 1700s. And this corresponded with an almost total lack of sunspots on the sun. Now, there is generally believed to be, of course, major human-induced climate change, no question. But there are other things going on at an astronomical level, and the very cold period in Europe that was experienced coinciding with the sunspots, is this something that is going to be repeated? Is this common in the Earth's history? And we can hope to find this out by studying other stars that are like our sun, and observing a sufficient number of them to determine what fraction of those stars are in a Maunder minimum-like state. And what that requires is very accurate distances of large numbers of stars from which one can pick out those stars that look most like the sun, and from a statistical survey of all these stars, figure out whether there were periods in which, whether it's common for stars to go through this period like the Maunder minimum. Solar system, I'm sorry, I'm going to just show that one again. What was it, 3-4 years ago, a big surprise, the first interstellar vagabond, the first interstellar traveler was observed passing through our solar system, something ejected from a nearby solar system, nearby stellar system. And several papers have now appeared using the Gaia data, trying to trace back the origin of this particular object, Oumuamua, which made the headlines in 2017. And if you want to figure out which stellar system this came from, you need not only an accurate orbit of Oumuamua, which we can measure from Earth, but you need accurate orbits of nearby stars and a model of the gravitational potential of the galaxy to allow one to be able to propagate backwards in time the orbit of Oumuamua. And there are now 2 or 3 candidate stars in our solar neighborhood which have been identified thanks to the accurate orbits of determined by Gaia, which may mark the origin of Oumuamua. A very important question, at least for astronomers, is, was our sun born in isolation? This would be very unusual. Or was it born in a cluster of other stars, which is the case for most stars. Most stars are born in clusters. If it was born in a cluster, where are our solar siblings? Now, it turns out, again, armed with very accurate orbits of the sun and armed with very accurate orbits of other stars, we can trace back the orbits of the sun and we can trace back the orbits of the other stars, and we can backtrack them for millions of years, and we can try and decide whether, try and ascertain whether there were stars which were born in the same star cluster as the sun. So this is the very first time that this has been possible, and one paper published already 4 years ago identified what they call solar sibling 1. It's now at a distance of about 1,000 light years, 360 parsecs, and it's something that has the same chemical composition, it has the same age and so on, and it was possibly or probably born in the same cluster as our sun. These are interesting for other reasons. If we're going to look for life, this may be a system in which life may stand a reasonable chance of being present. Solar system flybys, our sun and other nearby stars rarely collide. You can calculate, given the density of space, how long will it take for stars to collide. It would be something of the order of 1 billion times the age of the universe before our sun will collide with another star. But stars do make close flybys, and close flybys distort the orbits of the Oort clouds, these icy comets sitting far out in the solar system, remnants of the solar system formation. And what people are doing now is to look at the Gaia, the stellar orbits of the nearby stars, and calculating which of these are likely to have passed by the sun in the recent past. And we've got a number of candidates. One of these, Gliese 710, will pass 13,000 astronomical units from the sun in just over 1 million years. This again is of more importance than just simply saying it will pass or has passed nearby. It is believed that these encounters dislodge the Oort cloud comets and can lead to an increase in debris, near-Earth impacts and so on, cratering impacts, which have effects on the history of the evolution of life on Earth. Exoplanets, well, exoplanets are now known. There's more than 4,000 known, 3,000 come from transit surveys. I wanted to stress the point here that transits yield the planet radius in terms of the stellar radius, and you need the stellar radius to determine the planet radius. And Gaia is now determining these in very large numbers because the accurate distances are giving accurate models and accurate stellar radii. The at least 350,000 accurate stellar radii have been published already from Gaia DR1, and this propagates through into a mapping of the known exoplanet radii discovered by transit surveys into absolute radii from which densities and so on can be inferred. Just in terms of numbers, as I said, we know more than 4,000 exoplanets today. Gaia is expected to discover something of order 50,000 more just from its astrometric wobbles. You know, I'm going to go just a little bit faster because I want to allow time for questions. I just want to point out then, let me just pick out some highlights. The Hyades, one of the nearest open clusters. It's played a role in the history of the determination of the cosmic distance scale. Several hundred members are now known from Gaia. It shows prominent tidal arms. It shows a clean Hertzsprung-Russell diagram. Some, I think, very beautiful results are going to come out on the structure and evolution of the Hyades. The Pleiades, it was a thorn in the side of Hipparcos because the distance estimate from the Pleiades from Hipparcos was somewhat different from the distances that were coming out from more traditional methods. I think that's been clearly resolved from Gaia, and Gaia lines up its estimates of the distance to the Pleiades with all the other indirect methods that have been made, pointing to the Hipparcos results being a little bit of an anomaly for reasons that are not entirely clear. I'm going to jump over that one. Nearby stars, astronomers have struggled for decades to try and determine surveys of stars out to, say, 20 parsecs, 25 parsecs. Pre-Gaia, we knew of 5,000 out to 20 parsecs. The Gaia is defining a sample of around 300,000 complete out to a distance of about 100 parsecs. So an enormous advance in surveying the solar neighborhood. White dwarfs, very important endpoints of stellar evolution. Several thousand were known before Gaia. Gaia is throwing up roughly 80,000 within 100 parsecs. So these are going to be a very, very rich seam for observations of the physics and understanding of the physics of white dwarfs. Hypervelocity stars, just a few years ago, a very strange class of high velocity star was discovered. These are being ejected from tidal disruptions close to the galactic center, close to the black hole of the galactic center. The first one was observed in the early years of the early part of, I can't remember, 2003, I think. And Gaia has already pinpointed about 30 of them, some of them moving at more than 1,000 or 2,000 kilometers per second. These are moving at, you know, astonishing speeds compared to anything else we know in the galaxy. Even at 3,000 kilometers, 2,000, 3,000 kilometers per second, they will still be hurling outwards from the galaxy, and they will escape from the gravitational embraces of the galaxy in about 300 million years. Magellanic Clouds, I will just say briefly that we observed 36 stars in the Large Magellanic Cloud with Hipparcos and 11 stars in the Small Magellanic Cloud. The most recent data release of Gaia has identified 11 million stars in the Large Magellanic Cloud and more than 1 million in the Small Magellanic Cloud. So distances, motions, velocities, and so on are being determined for these. The same is true for a host of globular clusters surrounding the galaxy and dwarf spheroidal galaxies surrounding our galaxy. And my final view graph just on quasars. Just one quasar was observed by Hipparcos 3C273. Gaia is measuring more than 500,000. It's allowing us to define the reference framework of the whole stellar catalogue. It's also allowing some interesting advances in gravitational lensing of quasars. The final topic I will mention is the Enceladus stream. I showed you these large-scale cosmological simulations showing the galaxy formation as a result of tidal infall and filaments of dark matter. And some of these have now been identified in the Gaia data, and we're seeing direct evidence for the infall of stars that are the remnants of these stellar mergers, the most prominent one having occurred about 10 billion years ago. And they're still, the effects of that are still evident in the local velocity structures. So this is my final view graph, just a quick summary. Space astrometry, measuring star positions. We're not really trying to measure positions as such. We're using the positions to determine distances and motions. Space astrometry started with Hipparcos. Freeman Dyson, an eminent physicist in the Institute for Advanced Study in Princeton, said in 1988 that Hipparcos is the first time since Sputnik in 1957 that a major new development in space science has come from outside the United States. It's a nice byline, I threw it in. So Hipparcos opened the way scientifically and technically for Gaia. Gaia started as an idea back in '93. It was launched in 2013. It's operating today. It should operate until 2024. Final catalogues something around the year 2030. It is a big collaboration. I'm not listing here names of individuals, institutes. It's a pity because many, many people are devoting very significant parts of their lives to this project. And there are key players right the way across astronomy, technology, computer science throughout Europe, major institutes playing major roles. In the UK, I just mentioned briefly that the UK contributed the CCDs, the state-of-the-art CCDs from E2V, various other things as well. And there have been there are ongoing major contributions in the data analysis from various groups, including big groups at Cambridge, Edinburgh, and University College London. I'm going to stop there. It's a major scientific advance. Interpretation will continue for decades. And I thank you for your attention.
Well, thank you very much, Michael. That's been a tremendously packed talk. We'd better crack on with questions right away because I've got to bring this to an end by 9 o'clock. I'm going to start off with Charles Draper. Would you unmute yourself and ask your question?
Yes, thank you. Michael, fantastic talk, wonderful stuff and amazing what Gaia's producing. I've got a basic problem of understanding because I've got a 30-centimeter telescope and I know that its resolution limit is about 1/3 of a second. So how is it that a telescope main objective of a similar size on Hipparcos can get resolutions down to milliseconds, let alone the same thing on Gaia?
Oh gosh, there's always one who has a good question like that, isn't there? Now, look, the point is, it's a very, very central question. It's a very, very, very important question. And the key point is that the resolution of Hipparcos and the resolution of Gaia are not 1 milliarc second or 1 microarc second. What you are able to do is to centroid the point spread function of the image with that kind of precision. Yes. So you're absolutely right. The point spread function of Hipparcos was about 1 second of arc. And we were able to centroid that point spread function using a very, very accurately surfaced telescope with little chromatic aberration and everything else. And it's the centroiding that is the key part.
Gosh, wow. Okay, thank you.
Right, and now...
And Charles, I would say that during the development of Hipparcos, many astronomers would tackle me with that question and say, I don't believe Hipparcos can ever reach 1 milliarc second because lambda over d.
Yes, quite. Well, yes. That's what I was thinking. Yeah. Okay, thank you very much.
Thank you.
Jeff Wilson, then, would you like to ask your question?
Oh, thank you, Michael. Yes, I posed my question at the very start of your talk before all this fantastic information you've revealed, and it's a little bit trivial now. My question was in your introductory slide on understanding the stars, the first 2,000 years, you mentioned Tycho Brahe and Copernicus, but you failed to mention Galileo, and I wonder why. I mean, Galileo has always struck me as being central to astronomy, particularly the way the Earth revolves around the sun.
I think putting this talk together, Jeffrey, it is a tremendous challenge because the great problem is just the sheer wealth of information that I would like to have presented. I think one can easily fill a 1-hour lecture with the history of star positional measurements. And I've written, quite an extensive history, which is about 30 pages. And I think maybe to pick out Galileo. I mean, Galileo was I think there are many people that one could pick out in that long journey, and mea culpa.
Oh, well, perhaps Galileo was not as important as I...
No, I think it's not fair to conclude that at all, Jeffrey. I think it's a question of just picking out a few key developments. And, I think with Galileo, you always get into the question of who actually was at the forefront of the optical development, and Galileo's was an enabling technology, but there are so many others through the whole course of history. And I think when I've researched a little bit the history of it, I'm very conscious of how Europocentric we are in our view of the development of astronomy, and how critical the development, say, of the I mentioned briefly the Arabic world and the Chinese world and so on. And they were very important, not only for sort of theoretical contributions, but for practical contributions as well. So I think it's simply a matter of who to put in and who to take out.
Well, thank you very much for a really illuminating lecture.
Now I'd like to go to John Kemp, please. Can you ask your question?
Yes. I read something quite recently about Oumuamua, which suggested that there are some astronomers that are taking very seriously the possibility that it was an artifact of some extraterrestrial intelligence. And I was pleased to hear the mention of the fact that we've now got a few candidate stars for the source of those, for the source of Oumuamua. And I was wondering if any of these candidate stars had their own planetary systems, which includes a planet that might be suitable for life.
Actually, I can't answer that question. I think what will happen as the Gaia results become better and better, I think we will have a much better handle on the likely origin. And then I think it's a good question. I don't know the answer of these particular candidates. I would say from the reading that I've done on this object is that I don't think there is anyone seriously now, perhaps one or two people on the extreme edges, but I don't think anyone takes seriously that this is something to do with an alien civilization. I think there were, as it passed through, there were, the VLA was alerted to make radio observations just in case, but I think everything about it, the aspect ratio, I don't think there's the reflectivity and so on. There's no need and no evidence to suggest that it was alien manufacture. I think it's an inevitable byproduct of what we understand to be the method of formation of our own solar system and other solar systems. It's the debris that's hurled out, and there's going to be more. I think there's, I don't know how many there are now. I think are there 3? I'm not keeping up with the field, but I think we will see a better understanding of the origin, where it's come from, which system it's come from, as the Gaia data improves. But there's several papers written on that already. So thank you.
And now to Dick Bateman, please.
Michael, thrilling lecture. I'm always overcome by the complexity of the human mind required to even contemplate what you're doing with stars. My question is, with millions of stars noted, why only 14,000 asteroids measured by Gaia?
It's not 14,000 measured. What's happening because the satellite, can you see me? I'm going to wave my hands. As the satellite sort of spins and covers the sky, more and more observations are being accumulated. And depending on where these objects are in the solar system, the asteroids, at any moment in time, say now after the first 3 years of data have come out, some asteroids have been better covered than others, more will come out later on, improved orbits will come. I think it's only those 14,000 that have got reasonable orbits that have been constructed at the present time. So the final number, I think, is more likely to be in the area of 100,000 or so.
Thank you.
And they will be down to about 20th magnitude. I didn't stress this point. Gaia just measures everything down to around 21st magnitude in its own particular wavelength band. So anything brighter than that, it will measure. Anything fainter than that, it will not.
Thank you very much.
Right, we've only got a couple of minutes left. So Deepali, if you have a quick question, can you put that to Michael now?
Oh, hi. Well, I'll try to make it quick. It's just that I was delighted with the animation that TNG produced because what it's done is, after about 6,000 years, it's corroborated the visualization that happened all those millennia ago from the mountains of the Himalayan mountains, from the top of the Himalayan mountains, which gave rise to the theory of the origin of the material world in the shape of what was later adopted as the swastika symbol. That's actually a galaxy, you know. And what you demonstrated with TNG, in fact, was what was visualized by my ancestors on the Himalayan mountains through their observations over a couple of thousand years, which they put into maths. And the maths that you referred to, which originated 2,000 years ago with the Greeks and then brought to the West more recently by the Islam.
We've reached 9 o'clock now, and I did promise to end this by 9 o'clock. I think we...
All right, thank you, Deepali, thank you. Thank you.
Did I make any sense to you?
Yeah, yes. No, thank you. Illuminating.
Thank you.
And I'm just going to ask Judy's question very quickly. What happens to Gaia after 2024? That will be the last question we deal with.
All satellite missions these days are equipped with enough fuel to push them into some kind of safe or non-threatening orbit. As it is, Gaia is so far away, 1.5 million kilometers away from the Earth. It just naturally slides off into the depths of the galaxy. It's not one of these near-Earth orbits or geosynchronous orbit satellites that will decay and eventually fall back to Earth. No, Gaia will just as soon as one has finished operating it, the station keeping maneuvers stop and the satellite just drifts slowly into infinity.
Right. Well, I would like to say that this has been a wonderful tour through so much data gathering, information, new papers, theories being brought out. Clearly, Michael has rather scratched the surface here, but I mean, this is a very, very rich field. And it's particularly relevant in Bath because we can visualize William Herschel making his observations, and when he was doing what he called a sweep, which was using one of his telescopes to sweep across the sky simply through the Earth's rotation. And Caroline noting down all these observations and then managing the data. The amount of data they managed was seems huge, but what Gaia is producing is something else entirely. So what I'd like you to do is to unmute yourselves and give Michael the applause that he deserves.
Thank you very much. It's been a pleasure. Thank you.